Example here where we've got a little physics problem here. It's an example of an initial value problem. It's a generalization of the previous example on the handout where we're just going to be given a generic situation. We've got acceleration is a constant minus g. So g is the acceleration due to gravity. The negative means that it's directed downwards. We're going to be launching something off of the ground under the influence of only gravity. So we're ignoring any kind of air resistance. We're launching it straight up here vertically at a distance h units above the ground with an initial velocity v naught. And so using the acceleration here being a constant, acceleration negative g, we're going to work our way up to get an expression for the position s of t. So this is going to be one-dimensional vertical motion under the influence of gravity. And so the nice thing is we can use calculus to start with this basic principle and do calculus to get the formula that you would normally see in like an algebra book or an algebra-based physics class. All right, so here's how we do that. We got the acceleration is a constant minus g. So the first step to get back to position is to figure out velocity. And remember, the derivative of velocity is acceleration. So that means that the velocity is the integral of acceleration. We're integrating here with respect to time. So minus g dt. And remember here that minus g is a constant. So the integral of minus g dt would be minus gt plus a constant. And this is our velocity equation. Now to help us pin down what that constant is, we're going to use our initial condition. The initial condition is the initial velocity, v at 0, is the value v naught. So that means when I plug in t equals 0 to this formula, I should get v naught. And we can see here that the 0 there is going to cancel out that term. And we just get our constant is v naught. And so here's our initial velocity, or excuse me, our velocity function, minus gt plus v naught. And you might recognize that from physics. You're taking your, you got your initial velocity, and then as time goes on, you have your acceleration pulling downward. You have the acceleration there times t. That gives you the downward velocity, adding that to your initial upward, perhaps upward or downward velocity. Right? V naught could be plus or minus. All right. Now to get our s of t, our position function, remember the derivative of position is velocity. That means that the position is the integral or antiderivative of velocity. So we'll go ahead and do that. And we can use our sum and difference properties and scalar or constant multiple properties. We can rewrite this as minus g integral t dt plus the integral v naught dt. So now we can use the power rule here, the integral of t dt. Remember, think of that as t to the first power. So that's going to get, add 1 to that power, that's going to be a t squared divided by 2 plus a v naught t plus your constant. And once again, we can determine that constant by imposing the initial condition. Initially, we're launching this object from h units off the ground. So if I plug in t equals 0, I should get h. And we can see the terms that have a factor of t in it are going to cancel out. Oops, and that's going to give me my constant. I got this back. Excuse me, I got this backwards here. So I get my c is h. And so I get the formula that you probably see in the algebra books here, rewriting this a little bit we'll write a minus 1/2 gt squared plus v naught t plus h. That gives you the formula for a one-dimensional motion of an object launched from a height h, initial velocity v naught, vertical motion there under the influence of only gravity. And so that'll do it for that example.